All right, so in this video, we're going to be talking about how the average rate of change connects to the difference quotient, which in turn connects to the instantaneous rate of change, which we encounter in calculus. Now, the average rate of change and the difference quotient, it turns out, are actually just different ways of representing exactly the same idea, representing the slope of the secant line. So the average rate of change and the difference quotient are both expressions of the slope of the secant line. So recall that the secant line is a line that connects 2 points on a graph. Now, typically, when we're dealing with the secant line, we're dealing with a graph that is not a straight line. Although this does apply to examples that are straight lines, usually we're only interested in the secant line when the graph is in fact curved and we don't have a straight line that connects them. So the secant line provides that straight line connection between any 2 points on our graph. So just as an aside, we could draw a short example just to give us an idea of what's going on. So let's say I have some function and I have 2 points on my graph here and here, and then I'm going to try to connect the dots with a straight line. That secant line that touches the graph at 2 different points, that's the slope of that line is the average rate of change. So recall from our discussion of the average rate of change that our formula was f of b minus f of a divided by b minus a, which, again, the f of b is the y coordinate of our second point, the one on the right, and f of a is the y coordinate of the point on the left, the first point, divided by our 2 x coordinates in the same order. So the average rate of change is just the slope between those 2 points. Now, the difference quotient often is introduced to us in the context of just using and getting used to function notation, but it actually has a particular meaning. And the way the difference quotient works essentially is we're going to say that x is a and x plus h is b. So what that amounts to then is if I take b minus a, I'm going to be taking x plus h minus x, which is h. So this denominator for our difference quotient is just the difference between our 2 points. So they're separated by a certain distance, h. And then when you subtract them from each other, all that's left is that distance between the 2 points. And then x plus h, that's b, so this is f of b, and this is a, so that's f of a. And so again, we're just thinking about these 2 different points. Now, the difference quotient is a little bit more general because we can come up with an expression for the slope of the secant line that depends on 2 factors. It depends on both where the specific value that we choose for a, for x, and the distance between them. So we can change those values as we want. So we get a slightly more general case, but the difference quotient is essentially expressing exactly the same thing. Now, a question that comes up, particularly in calculus, is, well, let's say I want to know what the function is doing at a particular single point on the graph. Well, one way that I can try to think about that is I can make my secant line, but I can make the points closer and closer and closer. When they're very far away, they're not going to behave very similarly to a point on the curve. But when they're close together, then I'm going to get a much narrower window of behavior. So what happens if I let the difference between the 2 points get smaller and smaller? What happens if h goes to 0? Now, this is one of the reasons why when we're evaluating the difference quotient, our goal is to eliminate that h in the denominator, because if we put 0 in the denominator, then we're going to end up with division by 0, which is undefined. But usually when you calculate the difference quotient, there is a way to rewrite the expression so that you can eliminate h. And if you're able to eliminate h, then you can, in that denominator at least, it's still in other parts of the problem, but as long as you can get rid of it in the division, then you're good. And then you can plug in h equals 0, and you can ask yourself, so what is happening at a single point? And that is the instantaneous rate of change, is what is happening at a single point on the curve. What is the rate of change at a single moment, at a single point, a single value? Well, you can't calculate the slope between a point and itself. But when you use the difference quotient, you could get an expression for that slope that allows you to actually let h go to 0, and then you can calculate the instantaneous rate of change, what's happening right now. And again, you can estimate it if you calculate your average rate of change and you just let your 2 points get closer and closer and closer together. And then you'll see that what will happen is the average rate of change will tend to get closer and closer and closer to a particular value. And we'll do that numerical analysis in another video. But the idea here is that there's the connection between your average rate of change, your difference quotient. They're not actually different things. They're the same thing expressed in a different way. And then when you make those points get closer and closer together, this is when you tip over into calculus and you start getting the instantaneous rate of change, is what we're interested in calculus, not what's happening over a wide span of time, but what's happening at a moment.